Example 12.5, work and an engine cylinder. In a car engine, we're going to use the first law of thermodynamics to find the work done in an adiabatic expansion. Okay, in a car engine operating at a frequency of 1800 revolutions per minute, and that is 30 seconds or 30 cycles per second. High pressure gas against a piston occurs in about 10 milliseconds. So just to put that in context, the entire cycle takes 33 milliseconds, but they're saying that this part of the process where which is called the power cycle um, is 10 just 10 milliseconds. That is the part of the operation where work is actually being done to uh, give torque to the axle and stuff like that. So because energy transfer by heat typically takes time on the order of minutes or hours, it's safe to assume very little energy leaves the hot gas during the expansion. So we can say Q equals 0. So find the work done on the gas on the piston during this adiabatic expansion by assuming the engine cylinder contains N equals 0.1 moles of gas. Actually, an ideal monatomic gas, so degrees of freedom is going to be 3. That goes from, what's that say, 1200 Kelvin to 4000, no, 1200 Kelvin to 400 Kelvin, which are typical engine temperatures during the expansion. So here is my master equation, the one that's going to always be true, essentially. Um, and it's always true in the examples in this chapter anyway, because our N and R and degrees of freedom are going to be constant. So we can make the simplification here that Q is equal to 0. And then looking down here, we really don't know delta PV. We know, but we do know delta T. And so that gives us a chance to simplify it. We can say that the delta U is going to be equal to the work. So it's going to be 3 halves. Did they say? They gave us the number of moles, 0.1. And they gave us, well, we know that R is 8.31 joules per mole Kelvin. And our delta T is, okay, so I don't know where I stopped, but we basically know that we take this master equation, we can simplify it by changing Q to 0. We don't really have any idea what the change in pressure times volume is, but they did give us N and they gave us delta, and they gave us the temperature final and initial. So we can apply this equation and get work done in shrinking the gas is negative 997.2. The work done by the gas is positive 997 joules. So this says the work done on the piston comes at the expense of the internal energy of the gas. Basically, the delta U was negative 997.2 joules, and the work done by the gas is 997.2 joules. So those are equal and opposite. In an ideal adiabatic expansion, the loss of internal energy is completely converted into useful work. In a real engine, there are always losses. Now, uh, that's vague here because it seems like they're implying that the losses of the real engine happen during the adiabatic process. That's not really, there's very little lost in the adiabatic process. Oh, sure, maybe a little bit because there's going to be a little bit of friction in the cylinder. But where the loss really comes is because the big losses are going to come in the intake and the combustion part. During the intake, the volume, let's see, wait a second. Okay, I was about to show you this diagram, but it just got a lot weirder. You've got the intake where the number of moles is increasing. Then the cylinder compresses until it reaches a stage where the gas ignites. During the combustion phase, the volume stays roughly constant, and as combustion happens very quickly, increasing the number of moles of gas in the area. Then you have the power stroke where the volume increases while, and I think really what I ought to do is move this over here because that's gonna be about the same size. Let's do that. Okay, so this is essentially the PV diagram for an internal combustion engine. We have the intake where it's exposed to the atmosphere, so the pressure stays constant and the volume increases. Then we have the compression stroke, and during the compression stroke, all of the gas that's inside the cylinder gets compressed down to the original minimum size of the cylinder. Then we have the combustion where the gas ignites, creating a great big increase in pressure while the volume stays about constant. Then we have the power stroke, which actually does the work of pushing the axle around because we've got so much, and the pressure decreases as the volume increases. And then the valve opens and we exhaust the extra fuel and the spent fuel into the atmosphere, and then we're ready to do another intake. Now, it also might be appropriate for me to take the power stroke all the way down to here so that it reaches atmospheric pressure before it begins to exhaust. So we could have all of that available. And so intake and exhaust happen at the same pressure, which is the external pressure. Anyway, so the work done by the cycle is the area between this curve and this curve. However, we're getting a whole lot of energy from the potential energy in the I guess you would call it chemical energy available from the gasoline and petrol or whatever. So I just wanted to give an idea where it says in a real engine there are always losses. Where are most of those losses? There is a little bit of loss because these adiabatic curves are going to be affected by the friction of the cylinder, but the most of the loss comes from that exhaust part. The heat, the hot gas going out of the cylinder into the cold, out into the cold atmosphere. Question 12.5. In an adiabatic expansion of an ideal gas, why must the change in temperature always be negative? And I'm not sure if I'm going to give this the most intuitive answer, but I kind of have an answer for it. Adiabatic curves are steeper than isothermal curves. So if I was going to draw isothermal curves, let me use a colored pen for isotherms. If I drew isotherms in here, let's do another one from this point. And another one from this point. And so something like this. Okay. This is going between a higher temperature here to a lower temperature here. These lines represent the same temperature. So as the volume increases, you're always going to go from the higher temperature to the lower temperature. Um, these curves are n, r, t over v. So the higher the t is, it gives you, that tells you how far up you are on the isotherms. And I've drawn it wrong. Crap. These are supposed to be hyperbolas that actually come parallel with that curve, and they also come parallel with the the volume equals zero. It shouldn't cross that volume equals zero line, and it also shouldn't cross that pressure equals zero line. Um, but the but basically the PV to the gamma things are steeper than the PV equals constant. So what does this look like? PV equals nRT equals 0. What does the PV curve for temperature equals 0 mean? What does it look like? It looks like this. It is a straight line coming down, and it is a straight line going this way. This is the line of, so this would be the line P equals 0, and this would be the line V equals 0. If we go to PV equals 1, it looks something like this. And if we go PV equals 2, it looks something like this. And it just keeps going. This line always approaches V equals 0, and this line always approaches P equals 0. So it's a hyperbola. It's called the curve is called a hyperbola. And those are the isothermals. And notice that they always have a negative slope. That is, they're going down to the right. And the same thing with the adiabats. The adiabats are always sloped down and to the right. You can have a compressing adiabat or a decompressing adiabat. And you can have a compressing isothermal or a decompressing isothermal. And by combining those, you can get an engine cycle, which we'll discuss in a later chapter. But in the adiabatic expansion, which is this way, you got to push that way, the temperature is going from a higher isothermal to a lower isothermal. So the temperature is decreasing. So exercise 12.5, a monatomic ideal gas with volume equals 0.2 liters, and I'll write that as 0.2 times 10 to the negative third cubic meters, is rapidly compressed, so the process can be considered adiabatic. Adiabatic means the heat exchanged is 0. If the gas is initially at 101,000 pascals and temperature of 300 Kelvin, and the final temperature is 477 Kelvin, find the work done by the gas on the environment. Okay, so I'm writing down my big master equation, delta U equals Q minus, I've changed this to, instead of plus work shrinking, I'm subtracting work of the environment. This part of the equation is not going to be easy to use because we can't say delta PV is equal to P delta V. But this part looks pretty easy to use because we've got degrees of freedom, we've got N, we've got R, we've got delta T. So we could say work done by the environment is 3/2 times nr times the delta T is 477 minus 300. Trouble is I don't have n. So how do I find that? Well, I've got the initial temperature, and so I could use PV equals nRT for this to find n. N equals PV over RT, which we're going to have. I got 0.0081 moles. And now that we have the number of moles, we can plug that back into 3/2 times nRT, delta T, and we end up with getting negative 17.9 joules. So work is actually done on the gas in shrinking it. Are there other ways of doing this problem? Yeah, probably so. Let's see. We've got the initial pressure and volume and temperature, and both the initial and final temperature. So we should be able to find an expression for P final P final V final, which is equal to T final over T initial times P naught V naught. So I'm not trying to find P final or V final explicitly, but just trying to find the product of the two. And by finding the product of the two, it turns out it is 32.1 joules, and the initial was 20.2 joules. So the change in PV is P final V final minus P initial V initial, multiplying that by degrees of freedom over 2, which I have up here. Q minus work environment, we know that Q is 0, so 0 minus the work done on the environment is 3/2 times 32.1 minus 20.2, and 17.9 joules of gas shrinking. So same answer there, negative 17.9 joules gas shrinks. And finally, a third way of doing this problem is actually to try to integrate P times dV from the initial to the final velocity. And I might as well test this equation now. No better time than the present, huh? Actually, no, I don't think I will do that, because there might be a better time than the present, because I don't have an explicit value for the final volume in this situation. And I'll add a more explicit comment under here that it might be far easier to use delta U equals work shrink equals degrees of freedom over to delta PV or degrees of freedom NR delta T, rather than try to integrate over the volume. But that's what I did. To use the NR delta T, I had to first find the number of moles using the ideal gas law. To use the delta PV, I had to find P final V final using the ideal gas law. I did not actually explicitly find either the final pressure or the final volume. I only found their product.